Welcome back, everyone. This is where we ended the last time. We had a look at XRD, ChemScan data, assay data from the lab, and now we're going to go to HSC and convert this into a mass balance, a model fit, and then we can use the kinetics to model what will happen in an actual plant. So let's go to HSC. And this is something that I prepared a bit earlier just to save on time. So I went here to Flotation and I selected a unit icon and I just chose a lab cell, and it's as simple as once I've clicked on this I can go and put many lab cells in. I can go and connect them with streams, double click to end, etc. I'm not going to do that today. All we know is after I've deleted this, we had from Excel 8-minute intervals, 8 of 1-minute intervals. So I put in 8 reactors in series. We can also put in 10 reactors in series because the flotation data for one test might say 10, and in another test it only needed 3 reactors. And we can then use different data sets in the same model, one with using only the first 3 reactors, the other one using, all 10 reactors, etc. We'll get to that shortly. I've inserted a few rows. So this starts on row 26, the first concentrate stream, and you'll see why shortly. So we're in HSC Sim. I will just explain one thing quickly. I renamed the feed, double click and feed, and I did that for all the concentrate values, and then I had a tails at the end. You can leave it as stream 2, stream 3, stream 4, etc. all the way through, but you will get confused. So please, for the ones you have data, give them names that actually make sense. Lastly, there's a stream connectivity visualization. Blue equals input, red equals output, black equals internal streams, and all these ones are connected properly and one flows into the next one. We are now ready to go to our mass balance bit, and then thereafter in the next video we'll go into the model fit. This will be a fairly long video. I might break it into 2. Let's see how we go. Let's open the mass balance, and this opens a nice wizard. And on the left-hand side of the screen, we have here the balancing navigator. And we're going to work our way from top to bottom. And eventually, there will be more icons at the top here, and we'll work our way from left to right. So we have 8 units. As I said before, if you have data for only 7 or 3, you can select it that way and not have to redraw the whole thing. Streams. There are 17 streams. One's called feed, one is called tails. There are our 1-minute interval concentrates, and the other ones have just names, and this is why you should rename the ones you have data for. Also importantly is that I renamed all these as solid slurry types. A quick word just on sample quality, and so just to show the impact of that. If we have more or less confidence in our chemical analysis per stream due to sample weight, due to, Fe is much more accurate to analyze for than silica as an example, because there are multiple peaks for Fe in the XRF, etc. So we can say Fe is good, this concentrate stream we had less mass, so it might be moderately accurate, and it will assign some sampling error to it and use that in the mass balancing or metallurgical accounting. We're not going to get that fancy today. Just to let you know, it exists. When you do this the first time, your screen will not look like this. These will not have check marks in. These will be added automatically as we go through the process. And again, when you do this the first time, you will not have all of these in. So I'm going to remove all these variables, and we start. And as you can see now, there's no assays anymore. Let's start from scratch. There are again some wizards. We can add elements from a periodic table, we can add minerals from the database, we can add variables one by one. So I want to add assay elements. The first one is called Fe, enter. The second one is called silicon, enter, etc. And I now want to add a mineral assay, and this one is called hematite, etc. And now we can add it this way, or we can choose to use these wizards. So we've done a few, but let's use the wizards because now you understand how to do it manually. We can go directly to the shortcuts. We have data in our chemical assays for magnesium, calcium, Fe, silicon, aluminium, sulfur. And we might have more. We're going to concern ourselves only with the major oxides today, but it might be that you specifically want to model how your sodium containing minerals behave, your titanium containing minerals, etc., depending on the ore going in, whatever. This will do us for now. Now we have to add minerals. And you'll recall I just typed in hematite. So why don't we do the same? We'll start with magnetite. There we go, we have a stoichiometric magnetite. We also have magnesite, lots of other things. I double click it and it's added. Let's do hematite. And I'm going to click on it once, then I'm going to go here, add to the list. And the mineral symbol is not hematite, it's just HEM. So our previous effort was unfortunately incorrect. We know that it contains quartz. We know that there's some calcite. There might be some dolomite. There might be some talc. We know that there's some sulfur, so we assume that it's pyrite, not pyrite, pyrite. There's our pyrite added. And we also know from the mineral composition that there might be some goethite. So we just add the stoichiometric goethite. Please note that there are two ones here. There's mineral ID 64 and 1797. They're both stoichiometric. I don't know which one to choose, so we're going to go for the first one. That'll do. I'm not sure whether that double click actually put it in the list, so I'm going to check. Yes, it is in the list, else I would have added it again. Okay, we now have a variable list, 15 variables, our chemical elements, and our mineral elements. And we now move on to the next one, size fractions. Quick discussion. This is lab-based data, cited tests. It's small scale, there's only one, and it's called bulk. But when you go on to pilot plant testing and you have enough concentrate sample after your 1 minute interval, you can do a size assay on those and do a proper mineral deportment as a function of size and time. And that'll be pretty cool. And once you've done that, you can call yourself a fancy process engineer working for an engineering firm, because you can then design a flotation plant because you have all the data you need. Well, sort of. I mentioned before you can have multiple data sets, so you can add a data set, clone it, etc. We're going to just use the default data set. Now, I've used this before, but it's as simple as pressing delete, and I have an empty data set again. Okay, so this is the data that I need to fill in for all the chemical elements, the minerals, and the tons per hour or grams per minute, whatever our measurement unit is. So I can now type all of this in from Excel, risking user errors, data entry errors, transcription errors. We're not going to do that. All we're going to do is we're going to say copy. I right clicked and I go to Excel. And I'm just going to paste it here. Now what I'm also going to do, I'm going to move it up so that the first concentrate is in line with the 1 minute first concentrate here. And then we'll deal with feed and tails shortly. So first part of the table, flow rate, that should be fairly easy to do, equals the grams we removed. And I can copy that down as a formula. And this I know is tails. And the very bottom one I know is feed or head chemistry. Now, we have not alumina, as is reported here. All aluminium is reported as aluminium oxide. We just have aluminium. So I'm going to use a little cheat here, but you can pull out your periodic table and molar weights, etc. HSC communicates with Excel, so I have a little add-in module that allows me to do this a bit easier. Equals the alumina in this line, divide by the molar weight of aluminium, divide by 2 because there's 2 moles, times the, why don't we do this differently? Divide by the molar weight of alumina, divide by 2 because there's 2 aluminiums, times the molar weight of aluminium. Enter. The first time you do this, it takes a little while, and thereafter it says, okay, this is not a threat to me. I can use this. And just like that, I have aluminium per stream. Pretty cool. Let's do calcium. Equals the calcium reported as CaO, divide by molar weight CaO times molar weight okay, that's simple. Fe equals the Fe, which is already reported as is. Magnesium equals MgO, divide by molar weight MgO times molar weight Mg. What error did I make? I did not include the quotation marks and it fixed it correctly. Sulfur equals sulfur, which is already reported in its elemental form. And lastly, silicon equals SiO2. And you know the drill by now, divide by molar weight SiO2 times molar weight Si. Done, pretty simple. Okay, there we go. We have successfully converted everything to elemental analysis. I'm going to drag the tails up to there, and I'm going to drag the feed up to the top. And then I can copy this whole table, I can copy that whole table, or I can just copy the values. I'm going to copy the values, copy, go back to sim, and I can go and paste the values in here, paste. But see, there's paste experimental. I can also, from Excel, copy as long as I have the headings and the stream names in, and as long as they match, and then I can paste experimental data And even if the column order is the wrong way around and these stream 2s to stream 8 is below the minute samples, it'll paste it to the correct row. Now we have some data gaps here. How do we deal with that? Well, there's this magic button called estimate missing values, and it is very tempting to press that now and fill in all the rest, which is a simple bit of metallurgical maths. The total feed was nearly 2000 grams. The first minute was nearly 500 grams. So stream 2, which is what remained in the reactor, would be roughly 1500 grams just below. And then I can calculate the chemistry for that. So we do it. We shouldn't, because it's over here on the right and there are other steps before that that we really should be doing. But let's just have a look because it's fun. Boom, we've calculated all the mass flows and elemental flows. Yay, it's that simple. However, it's better to do it later. So as fun as that looked, we can always just clear the estimated values, which is a sad thing to do, but we can do that. Or we can do it again. Doesn't really matter, but the manual clearly states don't do it now. What we want to do now is convert all these chemical elements to minerals. And once we've converted them to minerals, we can do the actual mass balancing. So I'm going to leave that for a second part of this video, just to keep the video short and make sure we record it successfully.